This screencast is about equilibrium with weak substances, so not really greatly ionizable, and in fact we're going to look at a thing called common ion effect. Alright, so the common ion effect is when you have a solution that contains both the acid and the salt that contains the second part of the ion from the acid. So if you look at this particular, we have acetic acid, and then you have NaC2H3O2. The C2H3O2 is the ion component that comes from when you dissolve your weak acid in water. So you can see, if you look down here at the bottom, you can see that you have your acid breaks down into the H, or the H3O plus, and then the similar salt. So we would say that this is the acid, and then this would be our conjugate base. So in a common ion, we have our acid, and then we have the conjugate base already together in the same solution. So the common component is the C2H3O2. What goes on here is when you dissolve these things together, you have concentrations or molarities that need to be added together or subtracted or taken care of when you're doing your equilibrium problem. So you're going to want to do an ice chart to navigate all this information, because you're going to have values on two sides of the equation now, instead of when we were doing strong acids, weak acids, we had most of our concentration was just initial, and then we adjusted it through the ice chart. But now we're going to have a number on both sides of the equation. We're going to have the acid, and we're going to have the salt, which is the conjugate base. And we're going to plug those numbers into an ice chart and calculate with changes, and do the regular part of an equilibrium problem that you've been doing all along. We have K, which is equal to the products over the reactants. And in this case, we're going to have more numbers to do. Here's a sample problem of a common ion effect. We have, what is the pH of a solution made by adding 0.3 moles acetic acid and 0.3 moles NaC2H3O2 to enough water to make 1 liter solution. So we're lucky here because they're telling us that it's a 1 liter solution, so we can ignore that, and instead of it being moles, we can assume that it is the same as the molarity. So you take your ice chart, and remember it's this acid plus water, which we do not include in our equilibrium expression, makes H3O plus, which is the same as our H plus there, and C2H3O2. We're going to plug in our numbers. We have our acetic acid concentration here, and our acetate ion concentration, and we are finding the pH. So the pH needs to be based on the equilibrium value. What we're going to do is we're going to change by some factor of x. Okay, so the x's, now we need to remember which ones are positive and which ones are negative. It doesn't indicate to here, but we can see a 0, so we know that we have to add x on this side. So we have x, and we have 0.3 plus x. And over here we have 0.3 minus x. And when we take our k, we will have x times 0.3 plus x over 0.3 minus x. Now, this is acetic acid, so we're going to be able to assume a known Ka value, which we can look up. The Ka value is 1.8 times 10 to the negative 5. You can look that up in most data tables for acetic acid. And then we're going to solve our problem. Now we know that at this point, doing the quadratic expression is not something we typically like to do. So let's look at our values. We have 0.3, which is an exponent of 10 to the negative 1, and our Ka is 10 to the negative 5. So they're far enough apart, we're able to make the assumption that both this x and this x will go away, because they're going to be so small that they're not going to make a great deal of difference in our concentration of 0.3. So we are left with x over 0.3, and on the bottom we have 0.3. And so if we simplify this problem, we can see that these 0.3's cancel, and so x equals 1.8 times 10 to the negative 5. Now we're not finished. This is our concentration of H plus at equilibrium, so our pH is going to be our negative log of the 1.8 times 10 to the negative fifth, or 4.7. Again, sig figs matter. We have only one. We have two sig figs, so we should have 4.74 as our resulting answer. So 4.74 is our pH of the solution that we make by adding acetic acid and sodium acetate. So you can see that the whole process is very similar to what we've been doing in the past. The only difference was this time that we had an additional concentration to include in our initial line, and we factored it just like normal with the x's. We set it up in a K expression, and we were able to make an assumption in this case to remove some of the variables and therefore make this problem easier.